Today, we're going to pull back the curtain on the hidden traffic cop inside your PC, the scheduler. Seriously, this thing is the only reason your computer doesn't just completely grind to a halt, and we're going to see exactly how it pulls it off.
I mean, really think about it. Right now, your PC is juggling this video, a web browser, probably checking for updates, and who knows how many other things in the background. It all feels so seamless, right? But underneath, it's just controlled chaos. So how in the world does your computer decide what to do next?
You see, every single thing your computer does, from moving the mouse cursor 1 pixel to rendering a huge video file, it's all broken down into these tiny little jobs called threads. And every single one of them is basically screaming for its moment in the spotlight, its chance to run on the CPU. Without a system to manage this free-for-all, absolutely nothing would ever get done.
So, to make sense of how Windows brings order to all this chaos, we're going to cover 5 key ideas. We'll start with the CPU's big juggling act, then get into the priority pecking order, figure out what a time slice is, see how tasks can get a temporary promotion, and then finally, we'll tie it all together and see why any of this matters to you.
Okay, first up, the CPU's juggling act. Let's look at how Windows even begins to wrangle all this chaos.
The hero of our story is the Windows kernel scheduler. Think of it as the ultimate traffic cop, or maybe a benevolent dictator, living deep inside the core of the operating system. Its one job, its only job, is to look at this massive, screaming crowd of threads and decide, millisecond by millisecond, which one gets to use the processor right now.
So, how does the scheduler make those lightning-fast decisions? Well, it's not random. It all starts with a very clear pecking order.
The scheduler's number one tool is a priority system. But, it's a little more sophisticated than just high or low. A thread's final priority is actually calculated. It starts with the base priority of the application it belongs to, that's the process, and then it tweaks that number based on the thread's own importance inside that application.
Okay, let's make this real. So a typical app you run has a normal process priority, which is a base value of 8. Now, if a thread inside that app is set to above normal, it gets a little +1 boost, bringing its final priority to 9. A below normal thread gets a -1, so its priority is 7. This whole system gives Windows really fine-grained control over what gets to go first.
And then you've got the big guns. On the scale you and I can access, priority 15 is basically the top of the heap. It's for time-critical threads, like for your audio playback, where even a tiny delay would cause a noticeable glitch. But get this, the scale doesn't stop there. Windows keeps priorities 16 through 31 all to itself for super-critical, real-time system tasks. These things are so important they can interrupt almost anything else to make sure the OS itself stays alive and kicking.
But here's the thing. Priority is only half the story. Just because a thread is really important doesn't mean it should get to run forever and hog everything. So that brings us to our next idea, how the scheduler enforces fairness using something called a quantum.
So, a quantum is basically a thread's turn on the CPU. It's the scheduler's way of being fair. Even a super high-priority thread only gets to run for a specific time slice. As soon as that time is up, the scheduler yanks it off and takes another look around to see if somebody else should get a turn. This is what prevents any one task from completely taking over your processor.
And this is where the scheduler's strategy totally changes depending on the computer. On your desktop or laptop, the number one goal is responsiveness, making it feel snappy. So Windows uses shorter time slices and gives a longer turn to whatever app you're actually clicking on. But on a server, the goal is just raw power, maximizing throughput. So it uses longer, fixed quantums to waste less time switching between tasks, because every one of those switches costs a tiny bit of performance.
Okay, now we get to the really clever part. The scheduler isn't rigid, it's dynamic. It can actually bend its own rules for the greater good of the whole system.
So let's imagine a classic computer science problem. You've got some low-priority background task that has locked a file because it needs to write to it. No big deal. But then, all of a sudden, a time-critical priority 15 thread wakes up and it desperately needs to read that exact same file. Now your most important thread is stuck, completely blocked by a task the scheduler thinks is unimportant. What happens?
This total gridlock has a name. It's called priority inversion, and it is a very dangerous situation. The scheduler's entire pecking order has been flipped on its head. The important work can happen, and the unimportant task holding everything up might not even get a chance to run to finish its job. The whole system can just stall out.
To fix this, Windows uses an amazing trick.
called Auto Boost. When the scheduler sees that high-priority thread stuck waiting on that low-priority one, it steps in and gives the little guy a temporary but massive promotion. This boost shoves it to the front of the line, lets it run immediately, finish what it was doing, and release that file lock. And the second that lock is free, the thread's priority drops right back to normal, and the important high-priority thread can finally do its job. It's an elegant solution to a really nasty problem.
And this kind of dynamic boosting happens all the time, not just for those emergencies. When you click your mouse or type a key, the thread for that program gets a little boost to make the interface feel instant. When a file finishes downloading, the thread waiting on that data gets a boost so it can process it right away. It's this constant, invisible dance to keep your system feeling responsive.
Okay, so let's bring this all home. Why does any of this complex, hidden stuff actually matter to you? How does this connect to what you actually see and feel?
This is the payoff. This whole invisible system is the reason everything feels smooth. The thread that moves your mouse cursor has an incredibly high priority, so it always gets to run. When some background task decides to kick in, the scheduler makes sure your game's critical rendering threads still get their turn so it doesn't stutter. This is the magic that makes a modern multitasking operating system even possible.
And this isn't an accident. This quote from the source material says it all. Client systems are tuned for one thing, interactive response time, while server systems are tuned for raw throughput. The scheduler's core logic is smart enough to adapt and serve both of those completely different goals.
So I'll leave you with this thought. The next time your computer feels slow, it's easy to just think, it's out of power. But now you know it might be something way more subtle. It could just be the scheduler, deep in the machine, making a calculated decision that, for just a brief moment, some other task is more important than what you're doing. It's not chaos, it's a very smart system making some very tough calls.
If you want to help me out, please smash that like button, leave a random comment, and subscribe if you want to become a better hacker.